Okay, so let's start now. So today I am going to give a lecture on the some topic of special topic in research and how the theory works to the experiment and how the theory has been developed. So today I supposed to give different talk, but since today I am going to present first regarding this thing, Gauss view and Gaussian would be required, very much required, and that kind of graphics and applications will come. So right now I started the lecture, probably up to tomorrow evening I will give the lecture in different time, and I will give little bit the information of the how the research, how the modern science, how the modern experiments are going on, especially in material science and in engineering, with the development of condensed matter physics, theory of the physics, just condensed matter physics or solid state physics, whatever. So today my presentation of the title is Introduction to Electronic Structure Theory. So in electronic structure theory means we would like to describe or discuss how the electrons, when revolving around the nucleus, what about their properties that would be reflected for the real material, real system, some experiment, whatever it is. For example, when they form some kind of bond, how the material will work. Many important things will come from this kind of electronic structure theory, and we will know the the electronic structure of particular material. It doesn't matter it is perovskite, it is 2D material, for example zinc oxide, it is 3D material, doesn't matter. Regarding graphene, how the graphene works, how the graphite works, why the properties of graphene and graphite are different, why the some particular material has different property than others, why the experimentalist observing this thing, and why the theory is different. So all this kind of information will come from the electronic structure theory. So before going to the electronic structure theory, let's see the what kind of methods have been developed during several times, and several moments, and there are many also history also there I will discuss throughout my lectures from right now to tomorrow. So let's see first that is called what is the definition of computational methods. Okay, people are saying computational method or computational method, DFT, that structure theory, what they are basically. So in terms of if you would like to tell what is computational method, probably this will be the best definition. Using some mathematical tools or approximation and computer algorithm to obtain some result relative to material science and engineering or material science particular problem, that would be our computational methods. So what we have to do, we have to develop some computational, of course, technique which is based on mathematical approximation and computer algorithm. Basically that is the computational method would be. And after, apart from that, there is called some computational quantum methods. Okay, so in that computational quantum methods which actually uh, focuses on different kind of equations that has been derived from the basic quantum mechanics, postulate of the quantum mechanics. When first of all today I was discussing about the band theory of solid, you will see that how the Schrodinger equation, how the Schrodinger concept came to the picture in solid state physics or solid state material and semiconductor material, like that. So in that cases, what we do, we have to solve the Schrodinger equation considering periodic potential. Similarly here, when we like to solve the such kind of properties or molecular properties or material properties, similar we will solve the Schrodinger equations. That would be computational quantum method, where we will apply the quantum mechanics, and that's why highlighted by blue color. We will try to solve the Schrodinger equation for molecular system as well as material system. And then we'll go to the ab initio quantum methods. So ab initio, this term, probably who are not familiar in that subject, they don't know. It has a different meaning. Okay, I would, when I'm going to teach ab initio methods, etc., it will come, which actually uses basically several methods that don't include any semi-empirical parameter or some experimental data or some experimental observation or some kind of extra parameter in that particular method. This is actually pure method. There is no empirical concept. That's why we say it is called ab initio methods. Okay, And finally, today you have enjoyed Professor Shailesh Kundarwar lecture, molecular dynamics method. In brief, sometimes we say what is called molecular dynamics method is called in brief MD method. Okay, is a computer simulations where we can analyze the physical movement of the atoms and molecules inside a particular region. That is called particular region. Sometimes we say simulation box. So that the atoms and molecules, how they are interacting, and it is allowed or not for a fixed period of time, that will give the evaluation or focuses of the system. It would be the main concentration of the molecular dynamics method. So molecular dynamics method, what will do, it will observe the basically kinetics of the atoms or molecules in a particular system. So basically, considering these things, computational methods, computational quantum methods, ab initio quantum methods, molecular dynamics, if you have the clear-cut picture in your mind, which are there, then you will realize what is this. Then let's see. And nowadays, there are different kind of scale, different types of system, where and which kind of method and how we will develop. There should be a clear-cut picture. Okay. If you look at my x-axis represent the length of the particular system where we have to study, and y-axis represent the time. Okay, at what time scale we have to consider. So basically, this scale sometimes we define multi-scale modeling methods or multi-scale modeling of materials. How to use different scale, different method. That's why multi-scale, different scale, different method. So when we are discussing of the order of Fermi level, if I ask anyone, what about the bond length, oxygen and hydrogen in water? Most of the people will say of the order of angstrom, 0.8 angstrom, 1 angstrom, something like that. The angstrom order means of the order of 10 to the power minus 10. That basis my scale or my anything would not work except this quantum mechanics. Okay, in that, or in other words, up to nanometer scale, Fermi to nanometer, we generally use the quantum mechanics. This is the method we have to apply, and in these cases, when we will focus on such kind of particular method, what will be there? We will try to understand the molecular level of origin, where the mostly like today's discussion, whatever we have, how the electron creates the covalent bond in solid, so that kind of analysis which should be focused on only electron. So in quantum mechanics, we will focus on the movement of the electrons and how the electrons is operating, how the electron is creating bond, and how the electron is determining the properties. It would be in quantum mechanics region. So in quantum mechanics, in this region, we say some kind of methods has been developed, that is called electronic structure theory. After that, we will go to the little bigger system of the order of micron. In that cases, the transition on the time of the order of nanosecond instead of femtosecond or picosecond, where the quantum particles and electron transition happen. So in that cases, when we have the molecular dynamics region, in that region, what we discuss, how the atom and molecules are moving inside the some particular region. If you look at that, this is I highlighted by a a box. It is called simulation box. In these cases, we use molecular dynamics, and we can observe the movement of these molecules or atom inside the simulation box of the order of nanosecond or several nanosecond, let's say 10 nanosecond, 20 nanosecond, like that. And after that after that, when the system is increasing, if you look at the our system is increasing in x-axis, instead of micros, let's say some micron to micrometer to millimeter order. In that cases, we try to use mesoscale method, and this case is mesoscale particle, which is a mesoscale particle, a group of actually atoms, we generally consider in that cases. And after that, when they increasing the length, there would be another method is called macroscale method, and we use the element something. So this is called predict the behavior. In these cases, when we study such kind of methods, we can predict the behavior of the material from the first principle. First principle means what? We will come to the tomorrow's lecture, what is called first principle or whatever rest of the thing. Now what happened using this kind of, if you look at this slide and each and every point, using such kind of methods and idea, as well as y-axis and x-axis and the electrons, atom particles also, it will help to design new material or devices which will have lot of application in modern science and nanotechnology, especially the engineering sciences and material engineering purposes and technology purposes. So whenever we are now trying to develop new devices, first theoretically we generally try to analyze this thing. If theoretically we found that this structure is stable, then we generally perform that such kind of experiment. So basically this the slide represent multi-scale modeling of the materials. So if you know the how long your system, how big it is, what kind of properties you want to explain it, we can actually using this kind of multi-scale modeling method. So what kind of good thing for such kind of methods? Using this computational material science and engineering, whatever we are discussing here, it's actually a rapidly growing field in engineering sciences. And especially material sciences and material engineering, as well as condensed matter physics. And you can find that many faculty members of not only India and also abroad, rest of the other countries also, many big scientists, they are working on in this field. In that case, what we do, if you look at, there are many scientists are working the development of new methods. Now you're thinking what kind of method we have to develop. Let's see, if you really attend all the lectures, then you can imagine where we have to develop, okay, and where people are still developing. So just seeing only this slide, only one slide, you cannot imagine where we are working on that. The first one is this: all around the world, people are working on development of new programs, new methods, new algorithms, which are now every day are developing and maturing. And if you look at every day, the technology that yesterday I was discussing, the technology also is changing a lot. This is especially the computer technology, and computer technology are, super fast kind of technology. You can see that 2 years, 3 years back, computer nowadays almost useless. So you have to understand that few days back, let's say, I should not say few days, I should say few years back, let's say 5 years back, we used to habituate with the computer Core i3. Right now, who is using Core i3 Intel processor? No one. Because of the development of many technology, including semiconductor technology, semiconductor material, computers, that's is coming to the computer motherboard, that the computer are getting much more faster than like anything. And our computational material science and engineering branch, whatever we are discussing, as well as the condensed matter theory subject, that is actually basically it is not only condensed matter physics, it is interdisciplinary to chemistry. People say computational quantum chemistry. Theory physics is telling is theoretical condensed matter physics. And engineering science, they are saying material science. And some pieces also say is material science and engineering. This is computational material science. Anyway, this kind of computational methods, almost the limitless properties using such kind of method, whatever I discussed in past slide, we can calculate, we can predict, we can compare to the experiment. Among them, what is the most difficult question will come from the experimental side, that one structure, one material, whatever you are thinking to design, for example, graphene. Let's say we have the graphite. Now we have to synthesize the graphene in a single layer. And the question is that this graphene will be stable or not. So after performing a lot of experiment, might be you can synthesize this graphene in a single layer. That I gave the very simple example today. But if you have some complicated structure, this is a heterostructure, bilayer graphene, trilayer graphene, multi-layer graphene, then what will happen? I will give some lecture sometime today, or some slide I can show. When you have the multi-layer graphene, the synthesis process is not easy. And how to synthesize such kind of thing, that idea can come from this kind of computational methods and some subjects. And this study using computer algorithm and also theory development, or some applying some theory, what we can do, we can actually predict the thermodynamic stability, means the enthalpy you can calculate, and then give free energy you can calculate, energy you can calculate. If we find out that really this is the structure, in reality, if we get the negative energy, then we should say this structure is stable. And how much is energy required to synthesis, we can explain from that kind of theory or analysis. So what we study from that, mostly that equilibrium structure and transition structure is required. When some material has been formed or some reaction happens, something happen, always there should be unstable position, that known as transition state structure. And there are many kind of moments, quadrupole moment, dipole moment, and polarizabilities, which is very important. And in for magnetism, we can calculate the magnetic susceptibility using such kind of method, and magnetic permeability in magnetism also we can analyze, and hysteresis energy we can also calculate. And most of the important thing in reality, vibrational spectra, harmonic frequency, and harmonic frequencies, such can be such type of calculation. Raman spectra, spectra nowadays probably one of the powerful study to analyze many kind of experiment. Raman spectra, Raman spectra, then IR mean it's called infrared spectra. Many cases, nowadays the Raman spectra is using also for biological cancer application purposes. How to detect the tumor or malignant tumor? In that case, Raman spectra is required. In that case, also theoretically we can predict computationally this kind of Raman. NMR spectra, electronic excitation, and UV spectra, reaction rates and cross section, many others thermochemical data, as well as the electronic structure calculation, the equilibrium structure, and many other properties, for example, material properties, then Young modulus. So many parameters we can actually we can actually estimate from the computational study. So our motivation sometimes is maybe divert, but we can easily solve many kind of problem using our computational technique. But if we look at the little bit idea of quantum mechanics, I hope almost everyone has very good idea in quantum mechanics. Using the quantum mechanics, we'll try to track first problem, which is called quantum methods. Okay, let's say you have a very simple system, very simple. What kind of very simple? Let's say particle in a box. That is the basic quantum mechanics. And even nowadays, we take first year or BSc honors first year we study. And the Schrodinger equation, which is Schrodinger equation, everybody knows, is H cap equal to C E psi, which is one of the powerful equation in quantum mechanics. Uh, we generally use that H cap equal to E psi. To what is H? H is the Hamiltonian operator, and psi is the wave function. Today, when I was discussing your single well potential, that case is easily we can solve such kind of equation. I found that the energies are discrete, not continuous. Then the rigid rotator, quite difficult. Harmonic oscillator, single, one-dimensional harmonic oscillator easy. When we have increasing three-dimensional harmonic oscillator, the system is going to be more complicated. Particularly one-dimensional box is very simple. In two-dimensional box, complicated. 3D, it's more complicated. Then we move to hydrogen atom. So you can see that when we started the hydrogen atom, it has only one proton or the one nucleus and one electron. When it is revolving around the nucleus, is what happened. We have to write down this Hamiltonian in very complicated form, and then if we have to write in spherical polar coordinate, then we can get the energy eigenvalue, and finally you can get the also orbit and orbital concept. So like that way, Schrodinger equation is very easy. Fine. So whatever the example I'm giving, that is very simple. But if you think about that little bit, let's say the this is very complicated when we have more than one electron or many electron cases, many atoms cases, many molecules cases. When the system is little bit complex or complicated, then what happens? We need to make some simplifying assumption, of course approximation, and solve the Schrodinger equation numerically or something like that way. So when we will do the approximation or assumption, then one by one theory, one by one concept, one by one hypothesis, approximation will come, and accordingly one by one method will generate. So till now, I'm telling some cases it is still possible to get very accurate result, getting such kind of assumption. Also, some kinds we can get very crummy results. Okay, some cases it happen. It is not unusual that whatever you are expecting that it will happen theoretical and experimentally same, which is not. Some cases we observe that some spectra or some XRD data which is observed in theory and what you have obtained from experiment, both are very far. It may be possible because of this kind of many approximation, many cases. And second thing is that, of course, if we reduce the number of approximations, if we develop the real Hamiltonian real system, then what happened? The number calculation time will increase a lot. And to calculate such kind of things, we must have to have some very good quality of computer. And when such kind of computer is not like your desktop, not like your phone, not like your laptop, it should be a server. Now some server has also limit, and server is not enough, then we need very big computer, which is known as supercomputer. Probably you might know there are many supercomputers now in India. One is called CDAC in Pune. They actually have very good supercomputer. IISc Bangalore, they have also supercomputer. So using such, when we have such kind of big methods to analyze such kind of system, it is many electron system, the complete computation time will increase. When the computation time is increased and requirement is also increased, we said computationally this thing is very costly. So basically what, the cost of the calculation increases when we increase with the accuracy of the calculation and the size of the system. Of course, if we have one hydrogen atom, so it is single electron problem. But if we have sodium, of course the number of electron is relevant. Okay, so it would not be easy, because the computational time which is required for your particular calculation, of course you need many resources. Okay, and that's why we see the computational cost generally enhance or increases depending on the size of your system and the accuracy of the calculation. Okay, so getting into the theory means how the electronic structure theory has been developed. Let me come to the particular one by one topic area. So getting into theory means there are many kind of theory, but we are trying to entering to develop some theory or to understand the developed theory, what long back people are have developed. There are three parts when we are going to solve the Schrodinger equations for many electron system. First one is called Born-Oppenheimer approximation. In brief, BO approximation. I'm pretty sure most of you knows what is called Born-Oppenheimer approximation. But what is the significance of the Born-Oppenheimer approximation? Everything I will teach in this lecture, so that everybody will have recap, or they will recap this kind of, will remind themselves what is called Born-Oppenheimer approximation. And what is the outcome of the approximation, which lead basically, when BO approximation leads the idea of the potential energy surface. In brief, PES, potential energy surface. And when we are expanding the main electron wave function in terms of new concept is called Slater determinant, that would be called theory or method. Okay, and that will be most complicated when we are writing in terms of wave functions. Okay, so it is not write down when I am going to teach this, what is this Slater determinant ABCD, then we realize what is called Slater determinant. Just for first day today, just to remember, it is called Slater determinant. What? We have to expand the main electron wave function, not only single determinant or normal wave function equation, it would be in Slater determinants. What is Slater determinant? I will definitely teach in my course. Okay, and this would be one of called method. Okay, and when we are writing this kind of wave function of a molecule, we have to consider there are let's say one molecule. Okay, let's say methane. It has 5 atoms, carbon 1 and 4 hydrogen. So when we are writing the wave function, what would be the wave function of the rest of the electrons instead of carbon? 1 carbon and there are 4 hydrogen. We have to write for all. Then we use generally linear combination of atomic orbital, in brief LSO, LACO, which is called, in terms of method, called basis sets. Okay, so representation of Slater determinants by molecular orbital, that molecular orbital which is basically are the linear combination of atomic orbitals. Okay, which is called basis set. So these three things is required for any computational methods which is based on quantum mechanics. Okay, if we go to molecular dynamics, today Professor Shailesh Kundal was telling that we have to define the force and force field parameters. Similarly here, when we are trying to approach in quantum mechanics, we have to use these three. What is this? Born-Oppenheimer approximation. Second is how to write down the wave function in terms of Slater determinant, oftenly we call method. And when we are writing the Slater determinant, we must have to consider the atomic orbitals to define one molecule, one material, whatever it is. It will be the linear combination of all the atoms in the system. Okay, so basically after that, what we'll do, we'll try to write down this wave function. If we know the Hamiltonian, we will get the energy. If it is the electronic system, if we consider in the atomic level, at the electronic level, we'll get the energy eigenvalue of the electron and the wave function. So what is this E? E is the energy eigenvalue in quantum mechanics. If we apply the electronic Hamiltonian, it would be EL, energy of the electron, and wave function is wave function. So let's see how to deal first term, the Born-Oppenheimer approximation, which is called BO approximation. So when we are trying to solve this time independent Schrodinger equation, this is the first way we have to write down. Okay, let's say we are writing the Schrodinger equation. It's like H cap, H hat psi equal to E psi. Very good. What is H? H is called sum of the kinetic energy plus potential energy. Some books write some other way. I don't care about that. Now, what is the kinetic energy of an electronic system? So the kinetic energy of the nucleus would be there. The nuclear kinetic energy we can write minus h cut square by 2 sum of 1 by m alpha grad alpha square. The alpha stands for here, I just wrote for the nucleus. Then the electron will come, the electronic kinetic energy. Very good. What is it? Minus h cut square by 2 me grad I square. Grad I stand for the electronic kinetic energy. Let's say we have many electron and many actually nucleus. Then what happened? The first term will come nuclear repulsion, which is noted by just Coulomb repulsion Z alpha Z beta E prime squared by R alpha beta. It is basically nuclear repulsion term. Then next term is coming nuclear electron attraction term. Why? Inside the nucleus there are proton, and outside the outside the nucleus, when the electrons are revolving around the nucleus, there are free negative electrons. That's why the first term is fourth term is nuclear electron attraction term. Okay, and the last term is coming electron repulsion term, because all equal type of charge repel each other. And what is the grad? Grad is coming for the 3D, which is basically grad square when delta 2 delta x square and something like that. If it is in one dimension, then it would be easy. The yz term would not be there. Then partial derivative of delta square by delta x square would be just d2 dx square. Very good. So the point is, if you look at the size of the Hamiltonian for many electron cases, it is not easy. If I give some particular problem to you, let's say you have chlorine molecule Cl2, or let's say you have sodium chloride crystal. To write down and to solve the Schrodinger equation, probably you may not be able to solve that thing. Or let's say I'm giving some example for graphene or graphite. If I ask to solve the Schrodinger equation, if I give another example, almost impossible to solve that such kind of equation, because you may know that it is not easy. Why it is not easy? There are many electrons, many nucleuses, many kind of interaction. How do I know such kind of interaction is there, and what would the value? Then we can write down in operator terms. So let's go to the first approximation area, which is called Born-Oppenheimer approximation. Very good. What is the approximation? Probably some of us know, but again I'm repeating here how to use this kind of approximation in our theory. Let's say the wave function of many electron molecule, which is a function of electron and nuclear coordinate. Very good. Here we know. So nuclear coordinate we generally write by capital R, or electron coordinate we generally write by small r. The motion of the electrons and nuclei are generally coupled. Everybody knows when the atoms are moving, nucleus also moving and electrons also moving. However, you have to understand that the mass of the nuclei, inside the nuclei or nucleus, there are many protons and neutrons, which are much heavier than electron. Okay, so if we assume that mass of the proton almost 2000 times of electron, this time Born and Oppenheimer, they are the world famous scientists, they started to do one approximation. If we consider the kinetic energy or revolving, which one is faster moving, they found that nuclei move much very slowly because of his heavy weight compared to electron. And it seems that the electrons inside this kind of atom, it seems the electrons are only moving and nuclear is at rest or fixed. This is the biggest approximation which opened the central role of the quantum theory and material theory and whatever the methods we are going to develop. What happened? It has a high degree of accuracy. What? During the transition, when these electrons are revolving around the nucleus, it seems that electron is only revolving or during transition and nuclear is at rest. Then we can approximate the psi of capital R and small r is a function of, it would be two terms. One part would be electronic wave function, another would be nuclear wave function, which is completely dependent on capital R. So psi El stand for the electronic wave function, and psi nr is the capital R is the nuclear wave function. So basically, what we understood, Born approximation open actually two things. One is that if we consider nuclear is at rest, then what happened? Nucleus is at means the kinetic energy of the nucleus is zero. So, and the wave function also he tackled in that way. The nuclear coordinate depends on, sorry, wave function which is associated with the nucleus should be independent of small r, electronic position, and capital R is the position of the only nuclear coordinate. So what happened here? So if we use this kind of strategy, okay, that approximation to ignore that motion of this kind of nuclear electrons, sorry, nuclear. So what happened? So this term basically invalid. We don't need this term. And some cases also we can ignore this nuclear repulsion part, and we can write down only this, and this term. So that is the beauty of the Born-Oppenheimer approximation. So after getting the BO approximation or taking the consideration of Born-Oppenheimer approximation, what we can write down for the Schrödinger equation? We can write down only the electronic part of the Schrödinger equation, which is H cap El, which is El stand for the electronic part, and psi El, which will give the electronic energy and the electronic wave function. Okay, so basically the Hamiltonian looks like this, which is first part is the kinetic energy of the electron, second part is the attraction part between electron and nucleus, the last part is electron repulsion part. Okay, so basically which leads, now if we write down, for let's say we have some particular molecule complex, let's say HGBr complex. Okay, if we increase the bond length, what happened? It will plot like this kind of potential, and it looks like this curve. Okay, this curve generally we see it in terms of some potential, we say Lennard type or repulsion per part. And what happened if we write down the total potential energy? One part is the electronic part, and second part is the nuclear part, which is this basically this. And when we plot this thing, it looks like a surface in 3D, and 2D to like a curve. Then its name is called potential energy surface. This is the concept proposed by the Born-Oppenheimer approximation. Okay, so here what we do, if we consider what the nuclear part also, it has also similar kind of Hamiltonian. Again, we are going to the potential energy sum. We can also solve the Schrödinger equation for the nuclear. So if we operate this H cap suffix n for the nuclear, it will work only for this region. What we will get, the energy eigenvalue for the nuclear part. Okay, so in generally this kind of spectra, probably we may know for the vibrational spectra, we generally observe many cases vibrational energy levels is like this. It is the example for hydrogen and fluoride complexes. It will be similar kind of potential energy surface, exactly like electron, and lots of vibrational energy level we can find out here. Probably you did some practical when you did some kind of master's program, or you will do, or you already done, or in your class you are also teaching to your student that this is called vibrational spectra. So what happened? The solution of the nuclear Schrödinger equation allow us to determine a large variety of molecular properties. Fine. An example for molecular properties is that vibrational energy levels, vibrational spectra. This is the way nuclear Schrödinger equation work, but our focus will be mostly the relation between the electronic part when we are dealing in the quantum mechanics. So this is the, you can see that this is the one of the example of potential energy surface for the one kind of reaction. I mean the oxygen oxidize, oxygen means nascent oxygen with the HCl, which form OH plus Cl. If we plot this thing in the bond and this in 3D, we'll see such kind of curve. In this region we can observe that oxygen and HCl, they are together, and finally they form a weak bond, and finally this is called transition state, and after that you will see it will form a molecule. And if we plot the energy, it looks like a surface. This surface is called potential energy surface. And we can also calculate the thermodynamic rate coefficient. Many things we can calculate using that equations or using quantum mechanical, and we will get some idea of the potential energy surface using just Schrodinger equation. So it's not easy to complete one day. Again, I'm repeating, I will give lecture frequently how to use this kind of quantum computational methods, and near future I also give very good application how we are getting such kind of property, which is most required for many purposes to analyze this experiment also. So right now again I'm coming to this method part. The method part, which is very important. I will continue that kind of discussion probably several days, how to develop the method and how to use this such kind of method to solve the Schrodinger equation for any kind of system whatever I mentioned. The electronic for the, let's say, more than one electron, we say many electron system, still it's not possible to solve the exact Schrodinger equation easily. So then what we have to do, we have to do many things. Okay, so let's first what we have to do. The first concept is that write down the Hamiltonian part. Again, I'm coming to same picture. The H capital first one is the kinetic energy of the electron. It's fine. If we know that the velocity of the electron of the order of velocity of the light, 3 into 10 to the power 8 meter per second, of the order of, I say, instead of 3 it may be 2, like that. And this second term is the electron nuclear attractive term, and the last term we're writing is the highlighted by red circle, which is the electron correlate, electron term. Okay, the electron interaction in reality, any material, any molecule, any system is very much complicated. Till now we don't know what type of exact electron interaction is going between in the crystal between two electrons. Or now let's say we have only one or two, three, but when we have the many electrons, this kind of electron interaction is the most culprit in to develop the any kind of methods and to analyze. And when we are not able to define properly this electron interaction, then we generally observe whatever you have done theory, you got some data, and what you have observed just opposite. That is the most weakest point in terms of theory. So if you have the better electron correlation term, then your method will give better result, which is consistent with the experiment. When your this term is not good, which is not consistent too much with the experiment, then some people observe, say, hey, what you are doing in theory, which is very fun. It is true what we are doing, but the theory is not easy like that. When we have to understand in experiment, we can observe many things. We have observed by our eyes, everything is correct. I am not denying any word, but the point is, are you able to develop this electron interaction term? I think most of the scientists, professor, engineers, as well as physicists, chemists will say it is not easy. Let come. So first, I will tell many things, also detail tomorrow about this determinant and methods, and probably I can also explain how actually this approximation leads the idea of this wave function when we trying to develop this kind of equation. So first we did the Born-Opperman approximation, when I explained the electron collision term, how it is difficult. So when we are going to the approximate the wave function, how to define the wave function of the electronic wave function. So as we discussed today, Pauli's exclusion principle, probably yesterday also discussed Pauli's exclusion principle. Professor Shailesh Kundalwalji also was discussing this thing, what is called Pauli's exclusion principle. We know very well. So no two electron can stay in the same quantum number, right? So here also similar thing, when we have many electron, we have to also consider that thing. So when we are writing after the Born-Oppenheim approximation, we are writing the next important approximation, the wave function. In generally, using just pure quantum mechanics, we write down the Schrodinger equation in terms of a basis of Slater determinant, which is basically sum of di phi. D is called the basis, which is d0 phi 0. We can expand any wave function in terms of basis in quantum mechanics. Then what happened? I will come to detail in also Slater determinant soon. And each and every electron might have either spin up, spin down. That is the Pauli's exclusion principle. But when we are writing like this very nicely, where is the spin? Then a wave function must be coupled of two things. One is called spatial function, means this phi is multiplication of the coordinate of which depends only the spatial part, mean x, y, z, spatial coordinate, Cartesian coordinate, spherical coordinate, like that. With the fourth quantum number will come, which is called spin quantum number. Okay, which is will be also associated with some function, let's say alpha or beta. Then if we really write down this kind of Pauli's exclusion principle, then we have to write not in the like plus like this plus d0 like not no. Then we have to expand in terms of one determinant, which is called Slater determinant phi 0 1 by number of root over this phi 1 alpha 1 phi 1 beta alpha beta what? These are the spin function. Either alpha for stand for up, beta stand for down, and we have to write for all the electrons in terms of determinant. When we have the phi small phi 1 is phi I is called spatial function, which is depends on only molecular orbital, depends only the coordinate part x, y, z. Then alpha times phi I or beta times phi are called the spin orbitals. Okay, and then the Slater determinant give the proper antisymmetric Pauli's exclusion principle in when we derive this kind of wave function. If we know then possible then every phi d0 phi 0 phi 1 should be also like that, phi 2 will be like that. So what happened then, expanding all this wave function and coupled with that basis will get the psi L. So of course I will go to in more detail, probably slide will see more how to write down this kind of Schrodinger equation with two electron approximation. Okay, so this is the way for us to generally study the how to approximate this kind of methods. And near future, of course, I will go details approximation. Right now, I am just trying to teach one by one. So if you have any question up to here, maybe just to learn using this few slide only, try to understand the subject behind that approximation, as well as how to write down the wave function part. So wave function part also is a very difficult compared to compared to some cases write down the Hamiltonian. So what happened then at this time, Hartree and Fogg, these two scientists, I will come to in detail some slide also later on how to describe this Hartree and Fogg approximation, and maybe some few slides will be repeated during the talk because I have to go and come, go and 1, 2 and 4 we have to do. So Hartree and Fogg, going to Hartree and Fogg, before that we have to go to Hartree's approximation also. So let's just start from here when we are going to develop some method. First approximation is called Born-Oppenheim approximation. Then we impose this Slater determinant and we wrote the Hamiltonian part. Right now, let's say how to write down the all the electronic configuration for one example, neon atom. Okay, so neon atom has ground state. If we look at it, has total electron is around 10. So if we write down this equation, the electronic configuration using the sp orbitals 1s2, 2s2, 2p6, this case is very good. It would be phi 0, which is just I described phi 0. Then what would the phi I? It would be then the electron has to move in other state. Let's say 3s1, then it would be 2p5. Then phi 1 might be one possibility, 1s2, 2s2, 2p5, 3s1. So if you can imagine, phi 1 has this configuration. So if we look at the all configurations of the electrons, it is not easy to explain easily. Is that correct? Am I able to understand you that what I mean? Let's say we have a ground state configuration of the neon electron is 1s2, 2s2, 2p6. Let this is could be your phi 0. If I write down the next one phi 1, phi 2, the wave function should be different. The wave function associated with the electron position instead of p5, sorry p6, the one electron from the p orbital will go to s orbital of the next 3s. So 1s2, 2s2, 2p5, 3s. So if we like that the all phi's, I gave you phi 0, phi 1, let's say phi 2, phi 3, it would be like not exact if we write down, right? If we write down the all possible, let's say next one is not 1 2 3 4 5, let's say 2 electron is there, 2p4 like that. So if we have the complete information of the phi's, then it will be possible to write down in a Slater determinant, which is basically not feasible. Then how to solve the Schrodinger equation considering this wave function? That case is we have to understand the science is coming as then Hartree and Fock both did the one approximation. They say no, consider only one approximation, which is the central or backbone of quantum methods, which is that Hartree-Fock approximation. Instead of considering many determinant of phi 0, only consider only one configuration, use single determinant. So Hartree-Fock equation depends only one single determinant, and then they will apply the variation principle method, which is energy for approximation of wave function will always be higher than energy of the true value of psi. Then another method will come is called self-consistent methods or self-consistent procedures. Find the optimal basis set for molecular orbitals for phi 0. The basis set also will come as important. And then each electron will see the C average repulsion of the remaining electrons. No instantaneous interaction. So what this means? This electron, let's say I have one electron, it will feel the one average interaction the rest of the electron. Using that this approximation, then what a Hartree and Fock first time was able to solve the Schrodinger equation and got the first time electronic energy using Hartree-Fock approximation. Later on, this approximation will come to be as a method we'll call Hartree-Fock method and Hartree-Fock theory. Very good. So if you look at the how they started to define that thing, I took actually different way to represent this kind of pictures. It's called orbital approach something. So Mulligan first proposed the charge. So if we analyze this charge of the electron, we have to consider the Mulligan charge. There are, of course, there are many other kind of charge analysis will come, which is called natural bond orbital, also charge analysis. But Mulligan was one of the famous scientists. He proposed one of the method to calculate the charge. Then what happened? So when we have n number of electrons, the total wave function should write multiplication of the each and every electron, and we have to write down the Slater determinant. So now you can see that I'm writing the same thing, 1 by n power of n factorial. Instead of phi 1 alpha 1, I am writing it is called chi 1. Chi 1 is just combination of the spatial coordinate as well as spin. So basically chi 1 means phi 1 alpha 1. Chi 2 means like that alpha 2 phi 1 alpha 2 like that. Like this way we generally write down the determinant, and it is follow the Pauli's exclusion principle. When the electron also revolving around the nucleus, the electron itself is spinning around this kind of axis, around its own axis. Let's say this is the axis and also spinning. So in that way we can generally is Mulligan and Slater also formulate this kind of matrix, determinant combination of Slater determinants. And finally the spin quantum number, which is s equal to half h cos, and operator s square will come, and they were able to solve the such kind of approximation. And Mulligan on the first time proposed the concept of orbitals, a molecular orbital which is nothing but a wave function which is associated with a single electron. That was his molecular orbital approach. The use of this term orbital was proposed by Mulligan in 1925. That we always nowadays we habituated orbital, molecular orbitals, okay, which is basically nothing but the wave function associated with the single electron. So we are looking for many wave function system, right, that contains several particles, and particles also we can assume that the Hamiltonian can be written as a sum of one particle, the total Hamiltonian. So let's say we have many electrons, so many wave functions. So Hamiltonian, we can write the sum of individual one particle Hamiltonian operators, and later on the wave function already showed multiplication of the phi I. So if it is operate, the sum of the all individual electron energy will be the total electron energy. It was proposed by the Mulligan and and Robert Sanderson in around this time, 1996 to 1966, like that way. So they got this for this kind of new theory. Mulligan got the Nobel Prize in physics. Okay, so this was the one of the molecular orbital approach, which is very much important. I think today might have many questions answering, and tomorrow I will start from here how to molecular orbital, because it's not today's single lecture. I have to cover many lectures, so I know almost everyone is tired. So let's do some question and answering. So is there any question?